The frequency resolution is defined as, let's call it df, equal to 1 over big T, where big T is the total duration of our recording. For the EEG data we've been examining here, we're told that big T is equal to 2 seconds, so the frequency resolution, df, is equal to 1 over 2 seconds, or 0.5 hertz. To gain some intuition for the frequency resolution formula, let's consider the case in which we collect t seconds of data. If the sampling interval is delta, then we collect big N equal to big T over delta data points. For example, for the EEG data of interest here, we collect N equals 2,000 data points. We know that the number of observations in the data equals the number of frequencies in the spectrum, where we now include negative frequencies. Both the data vector x and the spectrum vector sxx have length n. We also know that the maximum observable frequency in the spectrum, the Nyquist frequency, is fixed no matter how much data we collect. Remember that the Nyquist frequency depends only on the sampling interval. We defined fnq, the Nyquist frequency, as f0 over 2. Now consider the case in which we increase t, or equivalently, we increase n. As we collect more and more data, the maximum frequency remains fixed at the Nyquist frequency, while the length of the spectrum vector increases. We therefore need to fit more and more values within the same frequency range, between let's say 0 Hz and the Nyquist frequency, as we increase n. The number of points is increasing in this interval, while the Nyquist frequency is fixed. This observation provides some intuition for the relationship between the amount of data recorded, either t or n, and the frequency resolution df.